identity theorem, for example. Look at this. You have f and g, they are functions on the complex plane, they are differentiable on C, okay? Which they give the name holomorphic. Okay. They are differentiable just once, but we know that if they are differentiable once, we know that they are analytic. Okay, what happens if they agree on any open subset? Any, no matter how small it is, then they agree for the entire domain. Of course, in their domain of definition. What do you mean? So this open set, any open set, no matter how small it is, maybe from 0 to 10 to the negative 10, if they agree for a little bit, if the functions agree for a little bit, they cannot deviate after that. They cannot deviate. So it's like, of course, I'm using the real when we're talking about functions in a complex plane. If they are like this, and the other function is on the top of it for a little bit, they cannot leave each other anymore. They have to go all the way with each other. And if you think about it, it makes sense. Why? Because if they agree on a very small neighborhood, they are analytic. So they can be represented by infinite power series. So if they agree for a little bit, it means that the function derivatives and value at one point, they agree of the two functions. And if they agree on that one point, then okay, I can represent them by the same power series again, you know. So you have many results that are, like I said, the least are non-intuitive. Very interesting results. When you read them, it's like, wow, how this happened.
Professor, it has to be a subset, right? Like, it can't be a point. It cannot be discrete number.
Cannot be a point. Yeah, it cannot be a point. Has to be, because a point will match the function value, not the derivatives. But an open subset means the value and the derivatives at a single point, which is the sufficient thing. Yeah. An open subset, no matter how small it is, which is very interesting. Okay, so that's enough about C, but it's really beautiful. Everybody should go and take complex analysis, but we don't have time. Let's move on from C. So I'll talk about other spaces. So let's talk about vectors. So R2, Rn vectors. We failed to give them the structure of a field. Multiplication is not very interesting. We cannot multiply two vectors in R2 and get a vector in R2 in an interesting way. It's not interesting at all. So yes, we can add two vectors to get a vector. So it's closed under this definition. So it's a group under addition. But multiplication, no. We don't multiply two vectors to get a vector. But we can multiply by a scalar. We multiply by scalars, right? So the vectors, the intrinsic properties of vectors is what? We can add and have all the group thing here. And we can also multiply by scalar to get a vector. So this is the definition of a vector space. Okay, whenever we, like I said, mathematics is about extracting intrinsic properties and make a definition out of that. So vector space is a space that is closed under addition and scalar multiplication. And then you can add features to that space. Like what? Like you can add metric. Then we call it a metric space. What is metric? Metric is that your space has a function that takes two vectors and give you the distance between them, right? So it has to satisfy some properties in order for it to be a distance. One of them is that it has to be 0. It has to be symmetric, right? Because it's the distance between the points. It doesn't matter the order here or there. It has to satisfy triangular inequality. Some few axioms. Then we call it a metric. So it gives you the distance between these 2 points. Okay? Not all spaces have metrics, have distance function. Then we have normed vector space. So vector space, like vectors, but we have a norm function that takes a vector and gives you the length of that vector. It also has to be greater than or equal to 0 and has to satisfy some other properties like linearity. If you have constant here, it can go outside triangular inequality. A few axioms. Then we can call it a norm. Then we have inner product or dot product. If you don't like inner product, you can use dot product. We engineers are more familiar with dot product. So you have a function in your space that takes 2 points and gives you the dot product of each other. It's like the angle between them, right? So in this space, we can measure distance between points. Here we can measure length, right? Maybe length of curves. Here we can measure angles between vectors, okay? So actually, this guy is the higher thing. So if it's an inner product space, it's also a normal vector space. And if it's a normal vector space, it's a metric space. How? Because if I have inner product, actually this induces a norm. How's that? I can define the norm. I can define the norm of any vector x as the square root of the dot product of x with itself, right? And this is actually the way we define it for Euclidean space. How do you find the norm of x? Well, it's the square root of summation all its components squared. This guy is the dot product of x with itself, right? And likewise, if I have a norm, I can define a distance with respect to this norm. How? Because I can define the distance between any 2 points as the norm of x minus y, right? So, okay, so we got that. We got that if I have an inner product, this is the highest thing. It's like I have angles. The way I look at this is like we have spaces that don't have all of these. Sometimes I look at them like I hate to say this, but I mean in reality it's real anyway. You go to some places like some cities and the government is not interested in these cities. They don't develop, and you find it's everything is haphazard and you go to other cities and they are very nice and so and so. So it's the same here. It's like you go in poor cities or poor countries and you don't find something. Here you go to a little bit more civilized thing and you find like every point has it's like the ground is metrized. You can see the distance between all points. Here you can see the length of all these guys. Here you can see even the angles between vectors. It's more and more advanced.
Professor, I have a
sure.
question. So, can we say that the only difference between a metric space and a normed vector space is the existence of an origin or a zero element?
It's a subtle question. No, actually, metric space doesn't have to be a vector space at the beginning. So x is apple and orange with D defined as apple and itself is 0, orange and itself is 0, apple and orange the same as orange and apple is 1. This space with this metric is a metric space, very trivial and nothing, but it satisfies the definition. Metric space does not have to be a vector space. But yes, if you add the vector space structure, then you can say yes, the difference is the origin. So anyway, so these are the types of spaces. I will just add one more definition.